Hello everyone, welcome to the linear elasticity class. In today's lecture, we're going to discuss the kinematic of continua. It means that we're going to interested in covering the different parameters that would be used for describing the kinematics of a continuum. In the previous meetings, we already discussed the transition from the mechanics of particles to the continuum mechanics. And we drive the equations of motion or the equilibrium equation that would be used for describing the equilibrium of a continuum body, starting from the mechanics or the equations of motion of a discrete system of particles. So here we're going to discuss, in this video, we're going to discuss the kinematics of a continuum body. So in the beginning, let us introduce kinematics. We have discussed this once before. Kinematics is a branch of mechanics which is concerned with describing the deformation of physical bodies like solid materials. And again, the interest in this course or the focus is just over the solid materials and physical systems when they are subjected to some excitation. This excitation would be in the form of mechanical, electrical, magnetic, or even thermal excitations. So again, the kinematics that we are interested in the describing the deformation of the solid body. And we're gonna define here what does it mean deformation with more details. So for example, let us consider this simple example of a rigid body. Rigid body, it means that it is inelastic. It will not experience any change in the size or any change in the shape. Just gonna be with the same shape. It's gonna attain its shape or keep its shape all the time, but it would move from one location to another location. It would rotate. So it is rigid body motion generally. If a rigid body is considered, its kinematics is described by the displacement, by the velocity, and the acceleration that this particle or this object is going to do. And this is what you cover basically in the kinematic, in the dynamic class. In the dynamic class, you studied the rigid body motion, and we described, to fully describe the motion of this object, it should be fully described by a displacement, by velocity, and the acceleration. So we can say that the displacement, the velocity, and acceleration, these are kinematical parameters, that they are measure a specific physical phenomena related to this object that moves rigidly. So to describe the motion, this is a physical phenomenon. Motion, it is something physical that takes place or occurs in this reality. And to fully describe this motion, we need some measures. These measures should be good enough to describe this physical phenomenon. So to fully describe the motion, and this is what you have been told in the dynamic class, it should be fully described through displacement, velocity, and acceleration. So these are kinematical parameters, and this already covered in the dynamic class. The same thing is applicable in case that we do have a deformable object. Deformable object, or in other words, we're gonna say that this is an elastic body. Elastic body, it means that the object, it can do changes in its shape or size. It will exhibit some changes in the shape in addition to some motion relation kinematical variable. Like if you do have an elastic object, it is not rigid in this case. This object, it would move, it would rotate, it would deform. It means it would change its shape or size up on some external excitation or some external forces. So we're gonna say that this is also a deformable object, or the change in the shape in addition to the motion is also another type of the kinematical parameter that describe how much of a change that this object is going to experience up on or because of the external force. So generally, to describe the motion, we used to describe it through displacement, velocity, and acceleration. For example, the velocity was defined at the rate of a change of the displacement, and the acceleration at the rate of a change of the velocity of an object. So these are different kinematical parameters. But in addition to these parameters, in case that we do have a deformable object that is moving, so to be fully described, or its kinematic to be fully described, it's required to describe the displacement, the velocity, and acceleration. In addition, how much of a change in its shape that this object is going to exhibit up on the some external forces. In linear elasticity, and this is the interest of this course, we are working in linear elasticity. There are lots of kinematical parameter basically that should be used to fully understand or completely describe the deformation of an object. These kinematical parameters include, some of them are related to describing the motion, how this object already moving, like the displacement, the velocity and acceleration, and some other kinematical parameter that would be used for describing how severely this object is going to deform or change its shape because of the external force. So this is like in general are like two groups of the kinematical parameters. There are some kinematical parameters related to the motion, some other related to the change in the shape or the size and the dimensions of the object, change in shape and dimensions. The focus here definitely is to describe all of these kinematical parameters, especially the ones that are really related to the change, to describe the change in the shape of the object in the context of the linear elasticity. This is typically the same thing that you studied in the dynamics and in the mechanics of material class. In the dynamic class, the kinematical parameters were displacement, velocity, and acceleration. In the mechanics of material class, the kinematical parameters were displacement, were deformation, were the strain. So the strain, this is a measure. This is a very important measure to describe the change in the dimensions and the shape of an object. The velocity and the acceleration, these are also a very important kinematical parameter, but they describe how fast or the speed or the change in the position, the motion, describe the motion of this object rigidly. You got my point? So this is generally the what does it mean a kinematical parameter, and to study this kinematical parameter that we are not focusing so much on the force side as much as we are describing the motion, describing the deformation of this object. This is the meaning of the kinematic. This is one branch of the mechanics. The other branch is the kinetic. The kinetic is just relating the kinematical parameter to the forces acting on the object, and this is what we're gonna cover, especially when we discuss these stresses. So here I'm gonna bring to you some tips, some things to remind you with what does it mean deformation, what does it mean strain and stresses, these things that you had an experience before through the mechanics of material class. But to describe this thing, let me give you this very small or very simple example here. Let us assume that you do have a bar, this bar, that already fixed it from one end, and you decided for some reason to stretch this object with this bar with a tensile force, an axial force in this way as force P or F, whatever the name of the force. We can even give it a name like F, just a force. So this is simply a force. So what's going to happen to this object? This object, generally, if you don't have any continuum, because this body is just a continuum body, solid body, any solid material, if you subject this material to some external force, this force would be a direct force, it would be a moment, it would be pressure, it would be some thermal change. So this also temperature change. So this also is a type of a force. So generally, because of the forces, this object, it should do something, right? Or in other words, the force should do something in this object. So there are lots of things. One of the things, for example, like if we allow or if we didn't fix this bar is gonna keep flowing or is gonna keep sliding over a surface, kind of. So it means that we're gonna say that the force, it will result in some motion. It's gonna enforce this object to move. This is basically what you considered in the dynamic class. And even this object, it would be moving rigidly or it would be moving under some change in the dimensions. And this is what conventionally happens. This is what really happens. But the change in the dimensions in comparison to the change in the position, it would be very negligible. So in this case, we can assume that this object is just rigidly moved. And this is what you covered in the dynamic class. In the mechanics of material class, we are preventing the motion, the rigid body motion of the object. So we are acting, but we're still acting on the object with some forces. So these forces again should do something. This something here is going to result in some changes in the shape and the dimensions of this object. So one of the things, for example, and this is what you studied in the mechanics of material class. Let me just, like increase the thickness of this bar somehow to give you like more clear vision of this example. So again, it is fixed from this end, and this should be the bar, which is a little bit thick, in this way, and this is the external force. So because of the external force, definitely it will be stretched, right? So it will be elongated somehow, and from the lateral direction, which in this direction, assume this is like X and this is like Y direction. So along X direction, it will be elongated and there will be some changes in the length, like this is gonna be delta L, and where this should be like the L0, the original length. And the same thing applies for the width or the height of this bar, or the diameter of this bar, assuming that it is circular. It means that in the lateral direction it will result in it will experience some contraction, it will experience some decrease in the diameter, while we do have an increase in the length. And this is what you already studied in the mechanics of material class. This is very conventional. So again, what is the thing that this force did to this bar that it will result in some changes in what? In the shape or even in the dimension. In this case, this bar has been experienced a change in the dimensions only. There is no change in the shape, still bar, but elongated with lower diameter in the lateral direction. So it means that this force had been resulted in some changes in the dimensions. So here we do have change in dimensions, right? The dimension along x-axis, it will be different. The same thing applies along y-axis. It means that the force results in some changes in the dimensions. If we consider another example like this one, like you do have this square rubbery material like this, assume that this is like a rubber material, and this is like the x and y coordinates, and this is just a rubber material here. And for some reason, we're gonna subject this material into some forces, like this force F in this direction. Like it is like you holding this surface and just pushing it, moving straight, horizontal along the X direction. So this bar, it will experience some deformation, or this rubber plate, it will experience some deformation. So it's gonna take this shape, kind of, right? So initially it was like, you know, like a square. Now it had like a diamond shape. So it means that it changed its shape. So here we do have a different shape. Probably some dimensions would be the same, but the shape has been changed. So this is also a change of the shape, right? So all of these are different things, are results, or you know, something that this material is going to exhibit, whatever change in the dimension, a change in the shape, up on affecting with this material over this material with some type of force. For example, for this case, if we subject the material with a force in this direction, so we're going to have another changes, right? Or other changes in terms of dimension change or shape change even. So generally, any external force should do something to the solid material. Should do something to the continuum. This something, it would change in dimension, it would change in the shape, it would be change in position. Change in position, it means that you're gonna end up with some movement, like rigid body motion in general. So generally, deformation, all of these different changes in either position, like for example, if we consider, like assume that you do have a small box, like this one, and that this box is already over a surface, and assume that this box is somehow tall, kind of, right? Or whatever. And you're just gonna subject this box into some external force. So what's gonna happen? Definitely this box is going to move and it's gonna be displaced to another location. So it's gonna be located here, moving from position 1 to position 2, right? So it means that here we're gonna end up with some change in position, right, of this object. Also another example, how about if we do have this bar, for example, like this bar is already standing here and somehow it is pivoted. This is like a hinged support, and there is some external force acting on this bar. So, and there are some springs here, like there is a spring with a stiffness K. This is like, you consider lots of this example in the vibration class even, right? And for some reason, this bar, because of the external force, is going to be rotating. It's going to rotate here, right? So it means that after a while, it's going to, because of the external force, it's going to have like kind of rotation with an angle theta. So we're going to say that we have a change in orientation. orientation, it means that also this change in the orientation, it can be considered as a change in position. Like this point was here, now it became here. This point was there, so now it became here. So it means that all of these points are a changing position, or the overall continuum, the overall solid material has changed its orientation. It has been oriented, it has been rotated, kind of. So all of these are different changes. Because of what? Because of the external force. To describe these changes, you need some kinematical parameter. You need kinematical parameter like how much of displacement, how much of velocity, how much of acceleration, how much of a change in the shape, how much of a change in the dimensions. All of these are, to describe these changes, this is known as kinematics. This is the kinematical parameter that needed to describe all of these different changes. And all of these changes are known as deformation. So deformation, it is not just a change in the shape. It is not just a change in the dimension. Deformation in general is a change in position, change in orientation, change in shape, and change in dimension. Any changes that the object or the continuum body is going to experience because of the external force is known as deformation. All right? So simply, this is the meaning of deformation in general. And let us consider here. Let us consider this like continuum body. Assume that this shaded region, this is like a solid material for some reason. But this solid material, it is deformable, it is elastic. It means that it can change its shape because of some external forces acting on it, right? So assume that we have this elastic material, and let us pick 2 points. Remember that each one of these points is going to represent a particle. We said that this continuum, it is a composition of an infinite number of particles, and according to the classical mechanics, and this is what we're already using or working or considering through this class or this course, like each one of these particles is just a point. So if we're gonna talk, if we just pick, if we choose a point or we pick the point from the continuum, this point indicate a particle anyway. So anyway, we do have here 1 point. Let us assume that we do have 1 point which is just Q and another point which is just P point, right? And XQ and XB, these are the position vectors. This is the position vector for point Q. This is the position vector of point P. And DX, it should be like the displacement or the distance between these 2 points, kind of, all right? Or the position vector of point Q with respect to B. It is very similar to the thing that you studied before in the dynamic class. For example, if I ask you how much or even the kinematic course, the kinematics of machinery course, like you can consider that this is like a position vector because this is already a position vector here in this direction, and this is another position vector, but this one is a relative position of point Q with respect to B, moving from B to Q. It means that this dx, looks like it is the position vector of, this is the position vector of point Q with respect to B. So it looks like you're already moving from B to Q. And this should be the other position vector of XQ. If you remember from the kinematics of machinery class, we can write a loop closure equation to this position mechanism, or this is like a mechanism, right? To this position vectors, or all of these 3 position vectors. So we can say that if I ask you to write the loop closure equation for all of these position vectors, so you're gonna find that XB and DX, they are rotating in the same direction, and XQ in the opposite direction. So we're gonna have like XP plus DX equals XQ. Or simply, if I move this one to the right side, to the other side, we can say that the DX, which is the distance between these 2 points, it should equal to, or the position vector set up between these 2 points, equal the XQ negative the XB, right? Since I already defining this one as Q relative to B. Make sense? So it should be like Q relative to B, so it should be Q negative B, just take to the same order as already shown here. Anyway, this should be the displacement. This is the position vector, the relative position vector between points Q and P. Make sense? Very simple. So And let us assume that this is at instant of time t equals 0. Like this is the initial position. This is the initial configuration. So in the dynamics class, we're going to consider that this is the initial conditions, and after a while, because of some reason, because of some external forces, this object is going to be moving and is going to be seen at another location, at another point, at another like location. Yes, as I said. So it means that it will experience some movement, right? But this object, it would move keeping its shape as it is, or it would moving in the meanwhile its shape is going to change. And this is the case. Consider the general case that this object is moving, in the meanwhile it do changes in the shape. It was like kind of elongated here, it had experienced some changes in the shape. It has like more circular, right? So as you can see, there is a difference in the shape and difference in the location. It was like at position 1, now it has been moved to another location, another position, right? The same thing, it means that this object has been moved with all of its point. Like if we just focus on just the 2 points that we consider here, point Q, it has been moved and displaced to this position. And the same thing for point B, it has been moved and displaced to this position here, right? And this delta x uppercase, I'm gonna give this one as dx dash, for example, just to distinguish from this delta x or dx. This dx, this is the length. Assume that this is like a fiber, like a stick between these 2 points. So this stick, it has 2 possibilities. There are 2 options here. Like this object is going to move as it is, rigidly, with no deformation or no change in the shape. So this delta x will be keep still the same value as delta x dash. It means that there is no change in this distance. So if there is no change in this distance between the 2 points at the 2 different configurations, we can consider this is one configuration at an instant of time t equals 0 at position 1, and it has been moved to another position at another instant of time t, whatever this t is, but anyway it's gonna be higher than 0 definitely. At any other instant of time, it will experience a new configuration. So this is the initial configuration, this is the current configuration or new configuration of the object. But this is like a current or initial configuration. This is the initial configuration of the object, right? So if there are changes in these 2 configurations, in either the orientation or the position and the shape, it means that we do have deformation. Again, the deformation is described. The deformation describes 2 things. Describe change in shape, dimensions, change in position as well, or even change in the orientation, that it has been rotated, right? So as you can see, we do have all of them here. Like this object, it was elongated somehow. Now it has been experienced another shape. Also, as you can see, the distance between, or the stick setup between these 2 points, or the position vector between these 2 points has been oriented, even has been stretched somehow, like it has elongated somehow. This all of this indicate that there are some changes happen to this object because of the external forces. To describe these changes, you need deformation field, you need deformation measures, right, or kinematical parameters. And this is our interest through this video, just to describe all of these kinematical parameters. But going back again here, so this point Q has been moved to another location as Q dash. This is the new location of the point. The same thing for point B. So the displacement, which is UQ, this is the displacement that this point Q has been experienced. The same thing for point B. It has been displaced or moved by UB, which U is just a vector. This U also is a displacement. Both are displacement vectors, right? Vector, it means that it has 3 components, right? As we discussed before in the vector calculus. It means that this point is going to move like a displacement parallel to x1. x1 like this is x, and x2 this is like y, and x3 like z. You could consider this is like x coordinate, This is the y coordinate and this is the z coordinate, right? So it means that this point is going to move parallel to x, parallel to y, to parallel to z, and these are the 3 degrees of freedom that we discussed for any point belonging to the continuum, as we discussed before when we introduced the continuum mechanics. So all of these, let us talk here about these displacement fields, UQ and UP. From even the dynamic class, if you remember that the displacement, it is a change in position. Again, the displacement, it is the change in the position. Like for example, the position of this point, it was initially XB, it became, after deformation, it became XB dash. And the same thing for XQ. XQ became XQ dash. So if there is a difference between XQ and XQ dash, this means that this point Q has been moved. It has displacement. But if the XQ and XQ dash are identical, are the same, so there is no displacement. It means that this point Q is fixed point. It will not be moving, right? So generally, we can describe the displacement of any point as the difference between the position vectors at the 2 different configurations. So this is how much of displacement that this point has been experiencing. So we're going to say that the displacement of point B, it will be the XB negative XB dash. The same thing, UQ, it will be the XQ negative XQ dash. The difference between the 2 position vectors at the two configuration. This is like the position at configuration 1, this is the position at configuration 2, so we're going to end up with the 2 displacements. Make sense? So the displacement of a point is a description of the change in the position of a point. Simple, very simple. The change in the position of the point. Thus the displacement of points P and Q can be written as in this form, where X and X dash are the position vectors of the point before and after deformation. Before deformation, which is the initial configuration, this is after deformation. Make sense? Which is the current or the new configuration. If a rigid body motion, and this is very important statement, is the one in which all material particles of the continuum undergo the same displacement. However, a deformable particle is the one that in which the material particle can move relative to each other with different displacement. In other words, like they do have different displacement, then the deformation of the continuum can be determined only by describing the change in the distance between 2 points in the continuum, as I'm going to show you. So what does it mean this? For example, if we have this point Q and point P, both gonna be displaced or moving typically the same displacement. So we're gonna say that this object will be moving rigidly. It's just gonna change position. It was at location 1, then it has been moved to another location 2, and that's it. But there is no change in the dimensions. There is no change even in the orientation. Like, what does it mean? It means that, for example, the line between these 2 points will be still the same, just moving rigidly with no orientation or rotation to this line. So this is also a rigid body motion. This is the pure rigid body motion. The rigid body motion occurs only under one condition, that these 2 displacements, UQ and UB, are identical. Identical in terms of magnitude and direction. Remember that a vector, it requires 2 things, magnitude and direction, to be fully described, right? So for example, I may have both of them, they do have the same magnitude but different directions. There is deformation. This deformation will be in the form of rotation. It means that this bar setup, this dx will be rotated, will be the same as length, like dx value, the magnitude of dx, because dx itself, it is a vector. The magnitude would be the same, but the direction will be different. This one is directed this way, this one has another direction. So there is still deformation. There is no pure rigid body motion. Make sense? So the rigid body motion, the pure one, this is under only one condition, that the 2 displacements are identical. UQ, UB are identical together. So we're going to say there is no deformation at all. Make sense? But we're going to say that this object will experience some deformation as long as UQ and UB are different. So given this discussion, we're gonna say that we can here define what does it mean deformation field. So simply we can say that the deformation field, and we're gonna give it a symbol as F vector. So F, it is a vector. It is used, we use to describe the deformation in all the textbook of the continuum mechanics and linear elasticity, even or elasticity. We use to describe the deformation of the continuum as F, and it is a vector. So let us consider that this F stands for the deformation, how much of deformation this object is going to experience. So again, the deformation field, simply it is a change in the displacement. We can consider this one as the change in the displacement between two different points in the continuum. So what does it mean this? Again, we said that this object is gonna be rigidly moved with no deformation at all. There is no rotation, there is no change in shape, there is no change in dimension under only one condition. What it is, that these 2 points will be moving the same displacement, identical displacement. So just a change location, and that's it. But to us, there is no change in anything. There is no change in the orientation, there is no change in the dimension, there is no change in the shape, so there is no deformation. Make sense? Just a change in position, just displacement, with all the points are moving the same displacement, so there is no deformation. But when there is a difference in the displacements between any 2 points within the continuum, this indicates that this continuum has been experienced a deformation. Deformation in the form of rotation, in the form of a change in shape or dimensions. Make sense? So this indicates that simply we can define the deformation of the material or the continuum as simply how much of a change in the displacement between 2 different points belong to the continuum. Any 2 points, just pick any 2 points in the continuum. If there is a difference between the displacements of these 2 points from one configuration to the other configuration, definitely there is deformation in the continuum. Make sense? This is the physical meaning of deformation, very simple. So mathematically we can represent this deformation if we just choose any 2 points, like points P and Q, as we did here. So this point Q, it will be moving as UQ, and this one will be moving as UB. So simply I could say that the deformation F bar is going to be the difference between the displacement of point B negative the displacement of point Q. If there is a difference between them, there will be definitely some deformation. If there is no difference, there is no deformation. Very simple. We can even understand this expression. We can drive this expression very simple if we considered this delta x, the distance between these 2 points, and this delta x dash. So this is before deformation, this is after deformation, or this is at configuration 1 and configuration 2, right? So someone could say that the deformation, it should be related to how much of a change that this delta x, assume that this is like a stick, a steel bar, or a stick that is set up between these 2 points and configuration 1. Because of some external forces, this stick would experience some changes in the length or changes in the orientation, generally. So simply we can define the deformation. We can even, this is another concept, we can define the deformation as the change in the x before deformation and after deformation. So it's going to be the difference. If there is a difference in this position vector, in this vector dx, between configuration 1 and configuration 2, it means that there is deformation. But if there is no difference, there is no deformation. Very simple. So simply we can say that here, this is vector. And we already defined before dx as xq negative xb. So simply I can substitute, replace this dx by x. We said b first, right? It should be xq first. So it's gonna be like xq negative xb, negative dx dash is gonna be the xq dash positive because you multiply times negative, so it's gonna be like positive xb dash. Make sense? Then let us collect the xq's together and the xb's together. So this is gonna give us, we can just continue here. F vector is going to be xq, just collect the xq's, negative xq dash, right? Then plus, just collect the xb, so we're gonna have here the xb dash, negative the xb. I can carry on a negative sign outside here as a common factor, so this is gonna give us the xq, negative xq dash, right? Negative xq dash, negative the xb, negative xb dash. Make sense? Where simply we define that the difference in these two position vectors between the two different configuration, this difference gives us the ub and uq, right? As we define here, xb negative x dash, xb dash, and xq negative xq dash gives us ub and uq. So this indicates that this term, it should be the uq negative the ub. I'm sorry, the uq negative the ub. If we change it, you just change the direction of the deformation vector. Like if you said ub negative uq or uq negative ub, these two deformation vectors, they will be different, but different in one thing. Different in what? Different in the, okay. Yeah, so this is gonna give this vector, which is f bar, or this f vector. If we said that like ub negative uq or uq negative ub, they're gonna be the same in terms of magnitude, but different directions. We don't care about the direction for now. Anyway, the thing that you should understand about the deformation, that it is the change in the displacement between any 2 points that belong to the continuum between two different configurations or at two different instants of time. The initial configuration and the after deformation configuration. Before deformation, after deformation configuration. If there is a difference in this delta x or a difference in the displacement, this means that this continuum is going to experience some deformation. Going back again here, as I mentioned, the deformation, it is not just a change in the dimensions. It is not just a change in the dimensions. This delta x or dx and dx dash, they would have the same length as magnitude but different directions. So this means that this f bar, this f vector will have a value, will still have a value. Like for example, we can, if you remember from the kinematics of machinery class, we can write this vector in the exponential form, or even into x and y, or the exponential form that you're gonna have a magnitude and direction. Also, we're gonna have here a magnitude and direction. The magnitude, it would be the same, but two different directions will result in some f will have a value still. So in case that you do have dx and dx dash, both they do have the same magnitude. In case that they do have the same magnitude but different directions, we're gonna say that this object has been experienced rigid body rotation. It's going to rotate rigidly. There is no change in the dimensions. There is no change in the shape, but it's going just rigidly rotate. Like you giving it rotation and that's it. But if there is a change in the direction and if there is a change, if there is a change in just the magnitude, even the direction the same, so we're gonna say that this object experiences a change in the shape only, or a change in the dimensions only, but there is no rotation. Make sense? If the object experience, or there is a difference between the magnitude and the direction of dx and dx dash, both magnitude and direction are different, this indicates that the object experiences a change in shape and dimensions and rotation as well. But under only one condition, in case that both the magnitude and the direction of dx and dx dash are identical, are the same, so f will be 0 in this case. This indicates there is no deformation. Just simply the object moves as it is from one location to another location. There is no rotation, there is no deformation of the object. This is the physical meaning of the deformation. So simply, we can understand the deformation as a change in the dimensions of the object and orientations of the object or simply we can describe this one in terms of the changes in the displacement or the difference in the displacement between any 2 points belonging to the continuum. This is if we are working in the discrete form, in a discrete way. To make it continuous or to make it general, since we are talking about continuum mechanics, simply we can rewrite this form as the gradient or the derivative of the displacement, how much the displacement of any point is going to change from one location to another location. Like, because simply, if there is a difference here, this is the displacement at point P, there is a displacement at point Q. So simply, if we choose any point and we investigating how much of a change in the displacement of this point in comparison to any other point belonging to the continuum, this mathematically means the derivative of the displacement over space. This means du by dx. Like, for example, if we said that the velocity, like in the dynamic class, we was writing the velocity, for example, so this is f, we were writing the velocity as dx, or dx over dt, right? The change in the position over the change in the time. If we are working in the discrete form, this is equivalent if we said that dx by dt, which is the derivative, the rate of a change of the displacement over time, right? This is if we are working in a continuous form, like a continuous function. This is like a discrete function. This is like a continuum. This is like a discrete system of particles. Make sense? So if we defined here, all right, so if we defined here the change, this f is just the difference between, we could consider this is like the difference, or is somehow related to the difference between these 2 displacements with respect to, it should be like written like with respect to the delta x, the position, or anyway, no matter, just to, so you aren't gonna be confused. So simply it's gonna be the difference between these 2 points from that belong to the continuum. We can give it a more general form, like we can write this form as d, how much, or the way, describing the way of the displacement field of any point, how it changes with respect to x, where x, it should be like the position vector, or this is a vector, that this x, it should be this x vector, it should be the x and y and z, like you're gonna do partial derivative. This should be like a partial derivative to be more accurate, right? Like the partial derivative of u as a function of x, y, and z, which is, this is a displacement field, this is the displacement function. If you remember in the vector calculus, we said that simply it feels like a function that describe the changes or the displacements of the different points that belong to the continuum. Like, for example, if we are interested in the displacement of a point here, your objective is just to plug x and y and z into this displacement field vector. This is still a vector. With respect to the x vector, which it should be the position vector, with the x vector, it should be like the x or the coordinate vector, which is x, y, and z. Like you're gonna do the derivative with respect to the x, the derivative with respect to the y somehow. And if you remember from the vector calculus, simply the derivative with respect to x, this d by dx, or partial by partial x, this gives the gradient operator, right? Times v, we can write this one as nabla u, because nabla, it is partial by partial x, u, which is the displacement vector, right? So we can generally write the deformation that this continuum is going to experience because of some external forces as the gradient of the displacement. So this is known as the gradient of the displacement field. And this what defines to us the deformation in general. So generally the deformation, it expresses two main things: changes in dimensions and shape, and rotation. And rotation in the object, right? Rotation in case that we do have a difference in the directions, but they still the same magnitude. The changes in the shape and dimensions, you're gonna have both different magnitude and different directions. So we're gonna have rotation and the change in dimensions and shape. This is the meaning of the deformation and how we can describe it. So that's why this deformation is a kinematical parameter that describes the changes in the object because of the external forces. So that's why it is classified as kinematical parameter. Make sense? In addition to the deformation, there is a strain and rotation fields. As we said that the deformation, it can be described in the form of strain or changes in the dimensions and the shape or rotation. So we do have like two things. So that's why here we're gonna discuss two things as well. Like these two things are strain and rotation fields. This should be like S here. Make sense? Like we do have strain and rotation field. So simply, so what does it mean this? Based on my previous discussion, we can say that the deformation, it can be split into two things. A certain deformation parameter that just describes the rotation of the object, and this happens, as we mentioned, in case that we do have the same magnitude but different directions. Different directions. Under just this simple case, we're gonna have just rotation, right? Also, the other thing that we do have change in dimensions and a change in shape. This is what we're gonna call the strain. So the strain, it describes changes in the dimensions and the shape, but the rotation, it describes the rotation of the object, assuming that it won't gonna be experience any changes. Both of them together define name deformation. So deformation is the general term that can be split into two terms: rotation and the changes in dimensions and shape. The change in dimension and shape, this is what name the strain. Make sense? So the deformation tensor, it is a general tensor. If I ask you, for example, this F is the gradient of the displacement. So the gradient of the displacement, if you remember from the vector calculus, the gradient of a vector gives a tensor. So what does it mean? It means that this F here, so initially I defined this F like a vector initially, right? As a difference between 2 points, just to understand in the discrete way, it's gonna be like a vector. But originally in the continuous matter or in continuous material, it's gonna be a tensor. So it means that this F, it should be tensor, second order tensor, where this is the gradient of the displacement. And this second order tensor, the gradient of the displacement, it will have different 9 components. It means that this is a general tensor. If you just did the vector calculus to this gradient, we're gonna end up with 9 independent components, 9 different components of F, 9 different components of the gradient of the displacement. Make sense? Why? Because this is a vector and there is another vector. So for example, if we wrote this one, let me just have some space here. Okay, so we said that the F, which it should be a tensor, equals the gradient of u, right? If you remember from the vector calculus, the gradient, it should be like partial by partial xi delta I, and we are using the I index. We're still working in the same term, so we're gonna use like another index like j, for example, for uj delta j, and u is just a vector, right? It's just a vector. Then we're gonna collect these these terms, just collect the unit vectors together. So we're gonna end up with partial uj by partial xi delta I delta j. So as you can see, we end up with a tensor for F. So F is just a tensor, and I and j, these are the two indices, indicate the column and the row number, and these are the components, right? So generally, if we consider that this is a very general tensor, right? It's just a tensor. This tensor, it has 9 components. It has 9 components, and all of these components are different. They should be generally different, right? So it means that this F is just a general tensor. And the type of this tensor is a second order tensor, as we discussed before. Tensor. Also, we discussed before in the vector and tensor calculus that any general tensor with 9 components, even whatever it is, second order, third order tensor, or higher order tensor, but the focus through this course just over the second order tensors. For any second order tensor, it can be split into symmetric and skew symmetric parts, right? So if I ask you to drive or split this f into its symmetric part. So the symmetric part, symmetric part of the f, it will be simply 1 over 2 the f tensor plus the transpose of the same tensor, right? Very simple. It means that 1 over 2, just replace f with nabla u plus nabla u transpose, right? I just replace f with the nabla u. This is gonna give us, simply we can write this term as 1 over 2, nothing new, we just using the symmetrical definition or the definition of the symmetric tensor from a general tensor, right? So simply this is gonna give us the partial uj by partial xi, right? The delta I, delta j plus the transpose, you're just gonna have like partial ui by partial xj delta I, delta j, right? And then we can consider delta I, delta j like a common factor, so we're gonna end up with 1 over 2 the partial uj by partial xi, the plus the partial ui by partial xj and delta I, delta j, right? This is gonna give us the f symmetric, the symmetric part of the deformation tensor. Just keep this one on the side here, right? Then how about the skew symmetric? Let us do the same for the skew symmetric tensor. So this is the symmetric tensor. For the skew symmetric tensor, simply we're gonna have S skew symmetric. SQ, for example, stands for skew symmetric, equals 1 over 2 times the f negative f transpose, right? If we did the same manipulation, just plug f as nabla u and f as nabla u transpose, so we're gonna end up and do this manipulation. So simply we're gonna end up with this expression like 1 over 2 partial uj by partial xi negative the partial ui by partial xj. This should give us delta I, delta j, right? Which gonna give us the skew symmetric part of the same general tensor, but this is just the skew symmetric part. If we combine these symmetric and skew symmetric parts together into one tensor, we shall end up with the overall f. So f again is just a general tensor, second order tensor with 9 independent components that they are totally different, and it can be split into symmetric and skew symmetric parts. Going back again to the discussion here, right? We said that the deformation tensor, it is not just a vector, right? It should be like a tensor in this case. The deformation tensor generally, right? It can be split into rotation and the change in dimensions and shape. Or in other words, it fully describes both the rotation and the change in dimension and shape. The interesting thing that we're gonna find that the symmetric part of the f tensor, it describes only the change in dimensions and shape. But the skew symmetric part describes the rotation, the rigid body rotation of the object like it is rigidly rotate. This is the skew symmetric part. This is the interesting of the deformation tensor. Like the symmetric part will describe the change in shape and dimension, but the skew symmetric part is going to describe the rotation, just the rotation of the object. So here we're gonna find that this one describe change in dimensions and shape. Also, this part, it just describes the rotation, of the continuum object. Like rigidly rotate, is going to rotate. Like for example, if we consider this small square, like it is made of elastic material, rubbery material, and for some reason this square is going to experience some external forces, so it's going to experience some deformation. It means that this object is going to deform, it's going to have a different shape. Let's say that this is the new shape of the object. In addition, it's going to rotate. It's going to have like rotation. So it has been rotated. In addition, it has been, like deforming. So for example, to move here, like it has experienced some deformation. You could consider that initially it has experienced some deformations in the changes in the shape and the dimensions. Then it has been rotated. So there is rotation in this way. Like it would rotate first, then deform, or change the shape, or it would change the shape, then deform. So it has both of them together, right? So the rotation only to the overall motion or the overall change in dimensions and change in shape and rotation, it can be described by the deformation tensor, which is a general tensor. If we split this tensor into two parts, one symmetric, the other skew symmetric, this is gonna give us the change in dimension and shape and the object rotation, how this object is going to rotate. Make sense? This symmetric tensor is commonly known as the strain tensor. This is the strain tensor, which we're gonna give it a symbol as epsilon. And the skew symmetric tensor is known as the rotation tensor. This is the rotation tensor, which we're gonna give it a symbol as theta, indicates an angle. Theta, just an angle. So this is an angle of rotation, because to describe rotation of an object, you're just gonna measure the angle of rotation, right? So it's just an angle, this theta. So, and this is what commonly known here. So this is the physical meaning of a strain. The strain, it is the symmetric part of the deformation tensor. And the strain describes only changes in dimensions and shape, but it does not describe rotation, rigid rotation of the object. But there is another tensor that describes the rotation of the object, which is known as the rotation tensor or the rotation field, which is the skew symmetric part of the deformation tensor. Make sense? All right, so we can generally define, as we mentioned, that the symmetric part is commonly known as the strain, and the skew symmetric part is commonly known as the rotation. So generally we can define the strain, and still the strain, which is epsilon, this is epsilon, is a tensor, and this tensor is a second order tensor. Also, this is known as the rotation tensor. This is also a tensor, which is also a second order tensor. So for example, as we did here, as we did down here, the epsilon, this should be the symmetric part of the deformation tensor, which should be represented in this form as 1/2 the partial uj by partial xi plus ui by partial xj, and these are the unit vectors. So we can write this one as 1/2 as partial uj or j first, I first, it doesn't matter, like uj by partial xi plus the ui by partial xj, right? Delta I, delta j. Also, this can be represented as 1/2 the partial uj negative by partial xi negative the I with respect to the xj di dj, delta I, delta j, right? Yes, so this is going to give us the strain tensor and the rotation tensor. We can even write this one, like we can write this one as, or forget about this one, we're going to do it down. So let us investigate or write all the components. So how many components for this tensor? This tensor will have 6 components, but this tensor will have only 3 components. If you remember that we said that any symmetric tensor, it has 6 components. Any skew symmetric tensor, because this is a skew symmetric tensor, it has only 3 components, because the diagonal of the skew symmetric tensor is 0, and the off diagonal components, they are identical but of different signs. And the symmetric tensor, it has only 6 components, because the diagonal components, they are identical, but the general tensor, it has 9 components. So simply, if we combine 6 plus 3, this is going to give us the 9 components of the deformation tensor. So now let us write the 6 component of the strain in terms of the displacement. This is U, this is the displacement field, and this is known as the strain field. The same thing for the rotation in terms of the displacement field down here. So let us write these components in terms of the displacement. So simply we said that the epsilon as a tensor, it should be the 1 over 2 partial ui by partial, or uj by partial xi, plus the partial ui by partial xj delta I delta j, right? So if we remove the delta I delta j, this is going to give us the component. We are interested here in writing the component of this strain tensor. So we can simply write this thing as epsilon, because I can write this epsilon, as epsilon ij delta I delta j. It seems that, for example, if we remove delta I delta j with delta I delta j, we're just gonna end up epsilon ij. These are the components of the tensor. So we are interested in the 6 components. So we can say that the epsilon ij, the components of the tensor, are 1 over 2 uj comma I plus ui comma j. What is this comma? As we mentioned in the vector calculus, we can, instead of writing partial by partial x, we can simply use the comma. This indicate partial by partial xi, like comma I indicate partial by partial xi of uj, and comma j, this indicate partial by comma j indicate partial by partial uj of ui, or as already given here. So this is the compact form. This is known as the index notation. This is the index notation, or the strain in the index notation form. Like this is the compact form of the strain, and let us write the components in terms of x, y, and z. So I, j, k, it would I and j, each one it will be x, y, and z. So for example, for epsilon, for the case that I and j both are x, so we're gonna end up with epsilon xx. Epsilon xx, it means that both I and j are x. So this is gonna give us 1 over 2 ux comma x, right? Because both are x, plus ux comma x equals, this is gonna give us 2 will be cancelled with the half, so we're gonna end up with ux comma x. It means that this is gonna give us the first component of the strain along the x-axis, x epsilon xx. How about the epsilon yy? Assume that I and j are yy, so this is gonna give us 1 over 2 the uy comma y plus the uy comma y, which definitely gonna give us the same like uy comma y. So epsilon zz, we are expecting the same, right? It's gonna be like 1 over 2 the uz comma z plus uz comma z. This is gonna give us uz comma z. How about epsilon xy equals, epsilon xy, it should be 1 over 2. Now I'm using I as x, but j is y. So this is gonna give us 1 over 2 j is y, so it's gonna be uy comma x, because I is x, I'm using xy, plus the ui it should be like ux comma j, which it should be y. Make sense? This is for what? For who? For epsilon xy. How about if I'm interested to find epsilon yx? If I replace, just switch epsilon y. So this is like the transpose, right? Equals 1 over 2. Now I'm using I as y, but j is x. So this is gonna give us j, it should be x. So it's gonna be ux comma y plus the I, it will be y, so it will be uy comma x. Do you think that this value is different than this one? No, they are identical. It doesn't matter, just switch these two terms, right? But still the same value. It is half the addition of these two terms together. So what does it mean this? This means that epsilon xy is identical to epsilon yx. They are equal. So that's why this is a symmetric tensor. The off-diagonal component, this is the off-diagonal. These are the diagonal component, epsilon xx, epsilon yy, epsilon zz. These are the component that is going to be located over the diagonal. Because if we wrote this strain tensor in the tensorial form, and this is what you considered in the mechanics of material class, we was writing like epsilon xx, epsilon yy, and epsilon zz. The off-diagonal components, I'm going to use a different color. So we do have the epsilon xy here it should be epsilon xz, and there it should be epsilon yx, and here it should be epsilon yz, and this one should be epsilon zx, and here it should be zy, right? So these are the off-diagonal component, the green ones, and the diagonal component are the blue ones, right? So the diagonal component, no problem. The off-diagonal component, as you can see, epsilon xy, it should equal to the epsilon yx, and this is one of the properties or the important property of any symmetric tensor. So that's why the strain is a symmetric tensor. This component for a symmetric tensor, epsilon xy should equal to epsilon yx. The same thing, epsilon xz should equal to epsilon zx. Epsilon yz should equal to epsilon zy. And this is what we have proved here, right? Also, if we carry on and just continue for epsilon, for example, xz, so it's going to be 1 over 2. Now, xz, it means that I is x, z is y, j is z. So we're going to end up with uz comma x plus ux comma z. And if we try the epsilon zx, it will be 1 over 2 ux comma z plus uz comma x, which it should be the same. They should be equivalent, right? They should be the same value. They are identical. The same thing applies to the other epsilon yz, which is going to be 1 over 2 uz comma y plus uy comma z. And if you try the other way, which is zy, is going to give us 1 over 2 uy comma z plus uz comma y, which they should be identical. So that's why in general we do have 6 components, 1, 2, 3 components located over the diagonal, and 3 other components, 4 and 5 and 6, which will be distributed over the off diagonal of the strain tensor. And where you should understand that epsilon xy, epsilon yx, they are identical. Epsilon xz, zx, yz, zy. It means that if you replace the indices, if you switch the indices, you're still gonna end up with the same values. This indicates that in general, epsilon ij, it should equal to the epsilon ji, because why? Because this is symmetric tensor. Make sense? So this is for the characteristics of the strain in general. Here we are talking about just on the strain tensor. So it has in total 6 components, and these components should be distributed over the tensor in this way. And you should understand that the off-diagonal component, they are identical, they are equivalent or equal to each other because it is a symmetric tensor, right? So now let us discuss the physical meaning of these 6 components. We said that based on the previous discussion that the deformation, which is F tensor, this is the general tensor, right? The F tensor itself, it describes both the rotation and the change in dimensions and shape, right? And the skew and the symmetric part, just the symmetric part of this F is going to give us the strain. And the strain is going to describe the dimension and the change in the shape, but it will not describe any rotation, right? So let us understand these components. As I mentioned that these 6 components, they're going to describe a change in dimensions and shape. So it is 2 things, change in dimensions and shape. Some of these components, they're going to describe just the change in the dimensions. And some others will describe just the change in the shape of an object. So it means that even this component, I can split them into 2 different types of components. Some components, they can describe just the dimension change, and some other components, they're going to describe change in the shape. For example, I'm going to give you a very simple example here. If we consider this, just to understand the difference between a change in dimensions and change in the shape, let us assume that you do have this bar, and then we are fixing this bar here, and this bar is going to be subjected to some force as we explained before. So what's going to happen to this bar? Somehow, but we allow for like kind of sliding of this end, like this end is going to slide, freely to slide, that these points are free to slide in the vertical direction, but they won't gonna move in the horizontal direction. Or even, let us assume that we're just pulling from both sides. It is typically like we're already pulling this one from both sides. Anyway, so what's gonna happen to this bar? Just remove this fixed end to make it more general. And we're gonna have here this end in this way. We're just pulling this bar from both sides. So what's gonna happen to this bar? It will be elongated right here, and the lateral direction, it will be contracted, it will be just decreased in the size. So if you consider this is like x-axis and this is like y-axis, right? This was like an initial length L0, now it will attain a new length, bigger one as L. So we don't have a change, but a change in what? Change in the dimension. We had a dimension as L0, this dimension became another dimension as L, or another size, right? The same thing for the lateral direction. If we consider this is like D0, this is the original diameter, it will attain a new diameter as D. So there is a change in a dimension, but in the Y direction. Make sense? But do you think that this bar had been experienced any change in the shape? It is still a bar. It is still the same shape, but with different dimensions. Make sense? So it means that here, for this case, we do have only change in dimensions, only change in dimensions. There is no change in the shape, just dimension change. Make sense? Let us consider another case, but here it means that there is no change in shape. Make sense? Let us consider another example of this like plate, square plate, and for some reason we're gonna subject this one, it is like kind of fixed here, and it will be subjected to some force to attain another deformed shape. So this is gonna be the dashed line, this is gonna give us the deformed shape in this way. Here this object didn't rotate. It means that there is no rotation. Yes, there is a rotation here, but I mean that there are some points still fixed. It means there is no rigid rotation. There is a deformation in terms of change in the shape. Like this shape, it was a square, now it has a diamond shape, different shape, right? So it means that for this case, we don't have only change in the shape. We don't have here change in the shape. Definitely there would be some changes in the dimensions, but for example, if we considered our reference as x and y, like for example, this line, this horizontal line is still the same. This horizontal line is still the same length, so there is no change in the width or the height of the object. It means that the dimensions along x and y, there is no change in the dimensions parallel to x and y, but there is a change in the shape of the object. Make sense? So we're gonna say that we don't have a change in the shape only, there is no change in the dimension. So generally, up on deformation, up on affecting on the object with some forces, it would experience some changes in the shape, some changes in the dimensions, or both. In addition to the rotation, forget about the rotation for now. So that's why the strain tensor, all of these 6 components, some of them describe only change in the dimensions, and some of them describe only changes in the shape. The components that describe the change in the dimensions are the diagonal components, are only the diagonal components. These diagonal components, they describe a change in the dimensions. They describe change in dimensions. Because of what? Because of the external force. And the other components, the off-diagonal components, these ones, and definitely in addition to the other off-diagonal component, they describe a change in shape of the object. So that's why we give these components as the shear strain. These commonly known, these components commonly known as the shear strains, and these components are commonly known as by the normal strain. This is known as the normal strains. So you should understand here that the normal strain describes a change in dimensions, but the shear strain describes change in the shape of the object. right? So that's why we are splitting the strains generally into normal and shear strain. The normal again describe the change in the dimension, the shear strain describe the change in the shape of an object. These are the 6 components. So generally, so this is here, we're still talking about the symmetric part of the deformation tensor, which is the strain. The symmetric part describes 2 things, change in dimension and shape. 3 components of the strain describe change in dimension. 3 other components, which is known as the shear strain, they describe how much of a change in the shape of an object is going to be. Make sense? Even we can describe these components, we can represent these components over 3-dimensional elements, which is this element representation of the strain components. This is also one of the things that had been covered in the mechanics of material class. So, and according to the mechanics of material class, for example, for these 6 components, it can be represented over a cubic element like this one. So we're gonna have here the epsilon xx, and it should be going in the opposite direction from the other face like epsilon xx, and this is the normal strain parallel to x. This normal strain describes the changes in the dimensions of the continuum parallel to x direction. Like for example, if we consider like 2-dimensional square, and we said that we do have epsilon xx from this side and epsilon xx from the other side, it means that it looks like we're already stretching the object along the x direction. So this object will experience some changes in the dimension only, right? So epsilon xx, it changes the stretch or the contraction. If epsilon xx is negative, it means that it will be compressed. So it describes the stretch in case that epsilon xx is positive, or the contraction in the dimension parallel to x in case that the epsilon xx is negative. Make sense? So this is epsilon xx, this is the physical meaning of this component. How about epsilon yy? It do the same. It is epsilon yy, but along the y direction. It do stretch or contraction or a change in the dimension in general along the yy direction. Epsilon zz, it do the same. Epsilon zz, it describes the change in the dimension parallel to the z direction. These are the 3 components that located over the diagonal of the strain tensor. Make sense? How about the off-diagonal components? So we do have here, for example, like we do have epsilon xy. So epsilon xy, like you're already pushing this surface on the top parallel to x direction. This is epsilon xy, and pushing the other surface parallel to in the negative x direction as epsilon yx, kind of. And you should understand that epsilon yx and epsilon xy both are identical, the same value, they are equivalent. This is in case that we do have a positive, like you already pushing the top surface parallel to in the x direction, positive x direction, perpendicular, this epsilon xy, it should be perpendicular to y, epsilon yx perpendicular to y, and pushing in the opposite direction of negative x. So you're gonna give, like, if we consider a square, let us consider a square here again. And what we are doing here, using epsilon xy and epsilon xz, we are pushing in this direction for epsilon xy, and we are pushing in the opposite direction with epsilon yx, or even epsilon xy the same. So what's going to happen into this square? This square will be deformed, like you already pushing rigidly this surface into here and pushing this surface into this dimension. So there is no changes in the dimensions except changes in the shape. So we're going to have here a change in the shape of this object. Definitely there will be some changes in the dimensions, but over this plane, which is xy plane, because the epsilon xy, it works over a plane, but epsilon xx, epsilon zz, epsilon zz, xyy, they are working over an axis. So this is a change in the dimensions over parallel to x, change in the dimension parallel to z and y, but this is changing the shape of the plane xy. The plane xy was a square. After deformation, it became another shape. So the change in the dimension in the xy plane, this is a shear strain. So that's why this is a shear strain. It is kind of shear, right? The same thing applies to other shear components. So for example, here we're gonna have another component that is perpendicular to y but parallel to z. So this should be the epsilon yz. And in the opposite direction, we're gonna have the epsilon zy or yz. The same thing here, we're gonna have one component that is perpendicular to x but parallel to y, so it's gonna be the epsilon like xy, and in the opposite direction we're gonna have here the epsilon yx or xy. It doesn't matter, like this is gonna be for the strain, it should be like here epsilon xy, this should be like epsilon yx, so this should be here, this one should be like epsilon yx, right? And we're gonna have here the epsilon yx in this way. And the same thing, we're gonna have here one component that is perpendicular into this direction, so this is gonna give us the epsilon xz, and in the opposite direction we're gonna have the epsilon xz or zx component. So these are the 6 components, how they are represented over the a volume element, and this is what you covered or studied in the mechanics of material class. But the new thing here, we focus more on the physical meaning of this component. Again, the strain tensor in general, it describes the change in dimension and shape of an object, and the strain tensor is the skew, it is the symmetric part of the deformation tensor. And the deformation tensor itself, it is the gradient of the displacement. There is a general tensor that includes rotation and change in dimension, that include the rotation tensor and the strain tensor as well. Make sense? In these other figures, I've brought these ones from one of my papers. I published this paper in 2015. If you are interested, I can share this paper to you. What I'm doing in this figure, basically explaining the relation of these different components of the strain to the displacement gradients component, and distinguish between the strain and the rotation tensor through this figure. So I won't gonna go over it. Anyway, if you are interested, we can discuss this one in another. If you have any question or interested in this one, I can explain it to you. So this is for the strain. Now let us move to the rotation tensor, right? And let us investigate the different components of the rotation tensor. We said that the rotation tensor, which is theta, it is the skew symmetric part of the deformation tensor. We define this one as 1/2 the partial by partial uj by partial xi negative the partial ui by partial xj delta I delta j. Again, we can write this one as theta ij, where theta ij, these are the components of this tensor, and delta I delta j. So simply we can just consider this term as the components of the rotation tensor, typically the same what we did for the strain tensor. So theta ij, which are the components, it should equal to the 1/2 the uj comma I negative the ui comma j, which is just replace this delta, the partial derivative with the comma, right? For simple representation. So we can see that these are the components of rotation tensor in terms in the index notation, right? So let us figure out these components, find one by one. So if I said that how much is theta x so it means that both I and j are x's. So this is going to give us 1/2 ux comma x negative ux comma x, which definitely is going to be 0, right? Because this term is typically the same like this one, so we're going to end up with 0. And the same thing applies to the theta yy. Theta yy, it's going to be 1/2 uy comma y negative uy comma y, which definitely is going to give us 0 as well. Also theta zz, it should equal to the 1/2 uz comma z negative uz comma z, which definitely is going to be 0. These 3 components, these are the diagonal component, and they are zeros, and this is expected because this is a skew symmetric tensor. This is one of the properties of, or the characteristics of a skew symmetric tensor, that it has 0 diagonal components, right? So for example, as we mentioned, that this theta tensor, it's going to be represented in this way. It should have 0 diagonal component. Theta xx, theta yy, theta zz are zeros, but the off diagonal components, they gonna be with values like theta xy, theta xz, and here we're gonna have theta yx and theta yz, and then theta zx and theta zy, right? So this off diagonal component, they they do have values, but there is kind of relation between them. In the symmetric tensor, these two components, they were equal, but here for the skew symmetric, theta xy will be negative the theta yx. So they're gonna have the same value but different sign. So let us demonstrate this point. So if I ask you how much is theta xy, so it's gonna be 1 over 2 the uy comma x negative the ux comma y. But the theta, if you just see here, the theta yx is gonna be 1 over 2 the ux comma y negative the uy comma x. So as you can see, there is a difference in the sign. If you just put this one to the similar to like uy first, then ux, you have to have a negative sign here. This indicates that this one is negative, the negative of the theta yx, and this is, I'm sorry, the theta of xy, and this is the sum of the properties of the skew symmetric tensor. The same thing applies to the theta xz, is gonna be 1 over 2 u z comma x negative u x comma z, and the other side, the u z x is gonna be the 1 over 2 the ux comma z negative the u z comma x. Anyway, it's gonna be the negative of theta xz. The same thing for the theta yz equals 1 over 2 u z comma y negative uy comma z, and the opposite one, the other one is gonna be z zy, so it's gonna be 1 over 2 uy comma z negative uz comma y, and this should be y, and this should be theta negative the theta yz. Make sense? So as you can see, in total we have 6 components, but 3 of them are zeros. It means that in general the skew symmetric tensor, it has only 3 components. These 3 components are the negatives of the other 3 components. Make sense? So this is simply how we can represent, or these are the components of the rotation tensor. Now let us investigate all of these different components. So for example, how about this diagonal component theta xy or theta xz? Theta xy, it is a rotation about z axis, the missing axis. So for example, here you should understand that when we say that theta xy, this is rotation, or in other words, to be more accurate, this is the rigid rotation, because the object is going to be rigidly rotated. This is the rigid rotation of the object about z-axis. If we're gonna say that theta xz, so it's gonna be rigid rotation about the y-axis, the missing axis, and so on. For example, like the theta yz, it is related to the rigid rotation about the x-axis and so on. Make sense? So it means that these components, whatever the theta xy or the theta yx, both these components represent rigid rotations about an axis. Like you assume that you do have like a small plate or a square plate in this way, and you're just gonna give it rotation about the z-axis in this direction. Assume that this is the z-axis, and you're just gonna give it rotation. You're just rotating this one about the z-axis in either this direction or this direction, depending on whatever it is, theta xy or theta yx. Make sense? So we can somehow, so this is a tensor, and this tensor, it has only 3 components. And previously, we said that the thing that would have a 3 component is a vector. You got my point? Like, this is a tensor, generally it should have 9 components in general, but 3 of these components are zeros, and 3 of them are identical to the other 3, but except the sign, of different signs. So it means that this one can be simplified or reduced into just 3 components. It means that it can be somehow converted into a vector, right? And this is, yes, we can convert this rotation tensor into a vector of 3 components, but the vector of the rotation tensor is going to describe the rotation about x and y and z. And this is what we basically interested in, right? So simply, what is the relation between, or this is the tensor theta ij generally, or the theta tensor, which is represented in this form. This is a tensor. This is, again, it is a tensor. how we can convert it into the rotation vector. So this is known as the rotation tensor. To be more accurate, this is known as the rotation tensor. Can we derive from the rotation tensor a rotation vector? Yes. But we cannot do the same thing for the strain. This is just for the rotation tensor because it just has 3 components. So for the rotation vector, I'm gonna give it like theta vector here. Just to indicate this is the rotation vector. It's going to be 1/2 the curl of the displacement. Because why? What is this thing? What is this theta, the rotation tensor? The rotation tensor is the skew symmetric part of the gradient of the displacement, or the skew symmetric part of the deformation. And the deformation, it is a gradient of the displacement. So we can say that, generally speaking, on the side here, we said that theta tensor, it is the skew symmetric of what? Of F. Or it is the skew symmetric of nabla u, because nabla u is F. What is nabla u? It is the gradient. This is the gradient of the displacement, right? Of the displacement. So if we are referring to this displacement, the skew symmetric of a gradient of the displacement can be converted. This is going to give a tensor. To end up with a vector, it is equivalent to 1/2 the curl of the displacement. The curl, the cross product of 2 vectors gives a vector from the vector calculus, right? So this is a cross product of a vector, which is the gradient, another vector, which is the displacement. We're going to end up with a vector. So that's why this is known as the rotation vector. This is the rotation vector. Make sense? If we converted this vector notation into the index notation, or write the delta in terms of its component, the same thing for the displacement, we're gonna end up with 1/2 epsilon, or negative, there is a negative here, negative 1/2 epsilon ijk times the theta jk, where theta jk, these are the components of the rotation tensor. But theta, this is the rotation vector, right? The equivalent vector of the tensor, delta I. So as you can see, we're going to end up with a vector that is from the tensor. So for example, if we decided to work over these components, we're going to say generally, theta I, which are the components of the rotation vector, equals to the negative of 1/2 epsilon ijk theta jk, which can be written as the negative of 1/2 theta jk negative the theta kj. Or in other words, to multiply the negative inside, so it's going to be 1/2 the theta kj negative the theta jk. Make sense? This is going to be the theta I vector. So this is going to be the components. These are the components of the rotation vector. Make sense? So these are the components of the rotation vector. So the rotation, it can be described using a tensor, but in this way it will be represented like 6 components. 3 of them over the diagonal will be 0, and the other 3 will be the same but with different sign. Or we can simply convert this one into a vector. So this is going to be the rotation vector in terms of the rotation tensor, right? So simply we can write this thing like theta I, this is the vector, and theta kj or jk, since they are 2 indices, this indicates that this is a tensor. So simply, if I is x, I'm gonna write this one here, or just referring here. If I is x, it means that you are interested in the rotation about x-axis. It's gonna be the 1/2 of kj. So if this is x, k and j will not be x's, will be like y and z, because we do have I, j, k, which x, y, and z. So if this is x, this is gonna be like z, y, negative y, z. So the difference between y, z's and z, yz and zy gives rotation about x-axis, as we mentioned, the missing axis. The same thing, the difference between xz and zx is going to give us rotation about y-axis. The difference between xy and yz is going to give us rotation about z-axis according to this rotation vector. So this is the rotation vector in terms of the components of the rotation tensor. Make sense? So this is for the strain components and the rotation component, and generally about the kinematical parameter. These are the main three kinematical parameters. The general one is the deformation that describe both rotation and strains. And this one, it can be split into symmetric and skew symmetric part. The symmetric part is related to the strain. The skew symmetric part is related to the rotation of the continuum. And the rotation, it can be converted into a vector, just 3 components. The strain is 6 components. The diagonal component of the strain, which commonly known as the normal strain, they describe the stretch and the change or contraction or the change in the dimensions, but the change in the shape of over a plane, it should be described by a shear strain, which are the off-diagonal component of the strain tensor. Make sense? So this is for the rotation and the strain tensor in addition to the deformation. Let us consider this example as a practice on the things that we demonstrated above, starting from the displacement field, and I'm going to show you how we can calculate, end up with the strain components or the strain tensor, the rotation tensor, also the deformation tensor for this example, which is very similar to the thing that you covered before in the mechanics of material class, very quick. So we're going to go over this example, then we are going to move to the representing the strain components in the cylindrical and spherical coordinates. All right? So in this example, it is consider a solid body or a continuum that deforms such that the its displacement field is provided with this value. This displacement field again describes the displacement of any point that belong to the continuum. Like assume that you have a continuum in general. For example, if we are interested in finding the displacement of point A, your objective is just to plug the coordinates. This is like Z and Y and X. So your objective is just to locate where is the X and Y coordinates of this point and plug them here. You're going to end up with the displacement of this point, how it's going to be moving parallel to X, Y, and Z as a point. The same thing, it can be applied to any other point like point A, B, C, any point belonging to the continuum. This is the meaning of this displacement field. So simply, before even we start doing anything, if we are interested in the displacement of any point, simply what you're going to do, this is just a vector because it has delta X, delta Y, delta Z. These are the 3 components. So simply we're going to say that the UX component is going to be 2XYZ negative 4X squared Y. And this is the X component. The Y component of the displacement field is going to be the Y squared negative 2XZ squared. And the Z component, it's going to be the 2xz squared negative 3yx squared, right? As you can see, all of these components are functions of x and y and z. Again, if you just plug x and y and z for any one of these points, you're going to end up with the displacement along x and y and z of this point that belong to the continuum. It is required to drive the strain and the rotation tensors and then calculate the strain at a specific point like point 2, negative 3, 1. It means that this is the x component, y component, z component of that point, and then calculate the rotation of the continuum about x, y, and z axes that set up at point at this point, then represent the strain component over a volume element. It is very similar to the things that you have had before in the mechanics of material in case that the instructor had covered this part with you in the mechanics of material class. But anyway, we're going to go over it again, and I'm going to add to these requirements is to form the deformation tensor. So let us form the deformation tensor, the strain tensor, and the rotation tensor. The deformation tensor, this is what we're going to start with. The F, which is the deformation tensor, should be the gradient of the displacement. And the gradient of the displacement, if we decided to write this thing in terms of the index rotation or the components of this deformation tensor as Fij, is going to be the Uj comma I, which is the U, it should be like partial, if you just convert, so it will be partial Uj by partial Xi as we did above, or simply Uj comma I. So this means that, for example, if we are interested in the Fxx, the x component, so it should be the ux comma x. Your objective is just to differentiate the x with respect to x, the ux with respect to x. We have ux, uy, uz, so the ux differentiate this function with, find the derivative of this function with respect to x. So the first term it will be 2yz, the second term it will be negative 8xy. Very simple. How about the fyy? Do the same, the fyy. So it's gonna be the uy comma y. This is the general expression and we're gonna use it, right? Like fij, fyy, so it's gonna be uy comma y. So equals, differentiate the y with respect to y, so this is gonna give us 2y negative 0, right? Because there is no y's here. How about the fzz? Fzz, it's gonna be the same. Just it's gonna be the uz comma z, and we differentiate with respect to these to end up with 4xz and negative 0. There is no z's in this side, right? This is the diagonal component. Remember that the f, it should be 9 components. These are the diagonal component. How about the f diagonal component starting with the fxy, for example? So it's gonna be, according to this one, it should be the uy comma x, ij, ji. So xy, yx. Make sense? So the x derivative of y with respect to x is gonna be, the first term will be 0, negative, the second term will be 2z squared. Differentiate find the derivative with respect to x. Then how about the fyx? So it's gonna be the ux comma y, just switch the indices. Ux, the derivative of this ux with respect to y gives 2xz the first term, negative the second term will be negative 4x squared, right? We differentiate with respect to y. How about the fxz? The fxz, it will be the uz comma x, and uz comma x is gonna be the 4z, right? We are, no, comma x is gonna be the 2. It's gonna be 2z squared, because we differentiate with respect to x, negative the 6yx, right? And then this is for this one. Then we do have the fzx equal the ux comma z. So ux comma z is gonna be, the first term will be 2xy negative 0, because there is no z's in the second term. Then the last two components, yz equal the uz comma y, which is gonna be the uz comma y gives 0 in the first term, and the second term will be the negative 3x squared. So it's gonna be 0 negative 3x squared, and the zy is gonna be the uy comma z equals the uy comma z. The first term will be 0, the second term will be negative 4x z. So it's gonna be 0 negative 4x z. These are the 9 components. As you can see, we do have 1, 2, 3, 4, 5, 6, 7, 8, 9 components of the deformation tensor. Then we can set up them over a tensor. So this f tensor, we can write them into this tensorial form. So it's gonna be like the fx, fxx, and fxy, fxz, and here we're gonna have yx, and fyy, and fyz, and then we do have the fzx, and the fzy, and the fzz. And as you should understand that the fxy, it is not equal to the fyx. The same thing applies to all the off-diagonal component, 9 different components already given up here. If for some reason, if we block this point, and we are interested in finding the deformation of this point, these are the components of the deformation at this point. Just substitute for h, x, y, and z. At this point, we're gonna end up with the deformation of the continuum with reference to this point. Make sense? Now let us calculate the strain. How about if we are interested in the strain and the rotation tensor? Simply, this general tensor, it can be split into 2 components. One symmetric, the other one is going to be the symmetric tensor. So simply the strain component are the 1/2 ui comma j plus the uj comma i. It doesn't matter which comes first, ui or uj, anyway, because they're going to be summed. So your objective is this is the an index notation. So for example, the epsilon xx, it should be the ux comma x, right? And we already got it here. The ux comma x is this one. So it's going to be the 2yz negative the 8xy, as we got it before for the deformation. How about the epsilon yy is going to be this component, which is uy comma y equal the 2y. As you can see that the diagonal components of the strain are typically the same diagonal component of the deformation tensor. Why? Because the rotation tensor, which is the Skew symmetric part, is 0. If we sum the strain plus the rotation, this should give us the deformation tensor, and definitely this indicates that this diagonal component, which is of the strain, which are the epsilon xx, epsilon yy, epsilon zz, they're gonna be typically the same like fxx, fyy, and fzz, and this is what we're already getting, right? So if epsilon zz will be the uz comma z, which is gonna be this component as 4xz. The same thing, but how about the epsilon xy? The off-diagonal component, they're gonna be different than the off-diagonal component of the deformation tensor. So the epsilon xy should be the half of ux comma y plus the uy comma x equals. We already got epsilon uxy. So simply it's gonna be half the sum of fxy plus the fyx, because ux comma y, it should be this one, and the uy comma x, it should be this term, right? So your objective is just to sum this term plus this term times half. This is gonna give us the strain. So simply it's gonna be the negative 1 over 2, the negative of 2z squared plus this term, which is the 2xz, negative this term, which is 4x squared, right? And so on. If you continue like epsilon xz, it's gonna be 1 over 2, the ux comma z plus the uz comma x. Your objective is just to sum the off-diagonal component, the xz and zx for the deformation tensor, sum these two and multiply times half. This is gonna give us directly the epsilon xz. The epsilon yz, it's gonna be 1 over 2, the uy comma z plus the uz comma y. You can directly sum these two terms together times half. This is gonna give us the this diagonal component, and you should understand that epsilon xy, it equals epsilon yx, and epsilon xz equals the epsilon zx, and this yz equals the epsilon zy. Make sense? So these are the components of the strain. How about the rotation tensor? The rotation tensor itself, sigma theta xx, it should equal to the theta yy, it should equal to the theta zz are zeros. Because why? Because we demonstrate this one is 0. It should be the ux comma x negative ux comma x, which is definitely 0. But the off-diagonal component, this theta xy, it should equal to the theta yx equals 1 over 2 the uy comma x negative the ux comma y. If you mention xy, you should start with y here. So y comma x negative ux comma y, which is gonna be the 1 over 2 the fxy negative the fyx. Just observe the indices. The indices is a big deal for the rotation tensor. But it doesn't matter which come first in the strain tensor, because anyway they're gonna be added. But here, if we said that theta, forget about this term, forget about this one for now. If we said that theta xy, so we should start, if we're gonna use the displacement gradient, so it should be uy comma x negative ux comma y. If we decided to work with the deformation tensor, we should stick to the same order, xy, yx, because this one is uy comma x and this one is ux comma y. You got my point? So just take care of these index things. So simply we got fxy up there, right? Which is this one, and we got fyx. So subtract this one, negative this one. This is gonna give us the theta yx, which it should be the negative of the theta yx. Theta xy, it should be the negative of theta yx. So we're gonna end up with 1 over 2. The fxy, we got it by the negative 2z squared, negative the fyx. The negative of fyx is gonna be negative 2xz plus 2xz, negative 2xz plus 4x squared. Make sense? So this is gonna give us the theta xy, which it should be the negative of the theta yx. The same thing applies to the other components. Like theta xz should be the negative of theta zx equals 1 over 2 the u, again it should be u z comma x negative u x comma z, and but in the meanwhile it is the f x z negative the f z x. Make sense? Then we can write plugging the fx and zx that we got up, we can end up with a value for this theta. Theta yz is going to be the same negative as theta zy equal the 1 over 2 the uz comma y negative the uy comma z, and this is going to be the half of the f yz negative the f zy. Make sense? Which it will be, you're gonna get it with a value. So as you can see, we have only 3 components. We can set up them into the rotation tensor as 0, 0, 0 over the diagonal, and we're gonna have here the theta xz, here theta xy, I'm sorry, xy, theta xz, and we're gonna have here the negative of theta xy or theta yx, and over this side we're gonna have the theta yz. Here we're going to have the negative of theta xz and the theta, the negative of theta yz and the 0 over the diagonal component, right? This is for the rotation tensor. If we are interested in the rotation vector, so simply the rotation vector, which is theta I, it should equal to the, as we define it, as negative 1 over 2, the epsilon I jk, the theta jk. Which if you decided to get rid of the negative, I can write this one as 1 over 2 epsilon I jk theta kj. Because remember that the characteristic of a skew symmetric tensor, that theta ij, it is the negative of theta kj. So to get rid of the negative theta jk is equivalent to theta kj itself. I can write this one then into this form as a half of the theta kj negative the theta jk. Make sense? So for example, given this one, we can say that the theta x is gonna be half of theta. The order, we should proceed in this way, like I, J, K as X, Y, Z. This is the order that we should consider. So if we said X, the J should be Y. The J should be Y. So it's going to be like Y, Z, negative the theta, ZY. You got it? This is, I'm sorry, Y, Z. The same thing here, this is for the theta x, theta y, it's gonna be the 1 over 2, the, I can even start with this one. What comes after y, it should be z, so it should be theta zx negative theta xz. You got it? This is how we can write this one. The theta z, which is rotation about z axis, it's gonna be 1 over 2, the theta, what comes after the zx, so it's gonna be xy, and we're gonna have here yx. These are the components of the rotation vector. This is again rotation about x-axis, and this one is rotation about the y-axis, and this is the rotation about the z-axis. Make sense? So simply, if we found, because these components of the rotation tensor, we already got them here. If you plug them into this expressions, you're gonna end up with the rotation vector, or the components of the rotation vector of this continuum. Make sense? So these are the different tensors. Simply, we got in terms, so we started from the displacement field. We did some derivative to end up with the deformation, the strain, and the rotation tensor and the rotation vector. If we are interested in finding the strain at any point like this point, your objective is just substitute for any x into all the 6 components of the strain. Plug x equals 2 and y equals -3 and z equals 1, which are the coordinates of this point. How about the rotation of the continuum? In this requirement, it is required to calculate the continuum, the rotation of the continuum about x, y, and z. It means that we are interested in finding theta x and theta y and theta z. These are the rotations about x, rotation about y, rotation about z. It means that we are interested in the rotation vector, not the tensor. But definitely we have to find the tensor components first, then we're going to use them to find the components of the rotation vector that set up at x at 2, -3, 1. Like assume that this is the continuum and we're gonna set up a coordinates as x, y, and z at a point. Like we're gonna set up like x, y, and z components. Assume that we're gonna set up these coordinates at this point, -3 and 1. So this continuum is going to rotate, right? This continuum is going to rotate about this point, about this origin point, with an angle of rotation at theta x, angle of rotation at theta y, angle of rotation at theta z. How much they are? We can find them by plugging x and y and z with the coordinates of this point. This is how we can read these rotations about x and y and z of this of a coordinate system set up at this point. Another option is that referring to the original, so this x and y and z, these are like new coordinates, but we can refer to the original coordinates, which are the x, y, and z of this, and just observing, assume that you're already standing here and you're just observing the rotation of this point 2, -3, 1, how it's going to rotate around x, around y, around z if you just plug these coordinates of the point in the theta x, theta y, and theta z that you already got them down here. Make sense? So this is a straightforward exercise on finding the strain, the deformation tensor, and the rotation tensor and vector from the starting from the displacement field. Once we find the displacement field, we can drive these kinematical components. So far we discussed the displacement, the deformation, the strain, and the rotation tensors. These are different kinematical parameters that describe how severely the object is going to be affected by the external force, right? And these are the most important kinematical parameters that describe the complete kinematic of continuum mechanics according to the linear elasticity or even nonlinear elasticity, right?